We are on the verge of a revolution in cosmology. New data from the Dark Energy Spectroscopic Instrument, or DESI, may indicate that dark energy, at least in the sense we have understood it until now, does not exist at all. And those effects we previously tended to explain by the existence of dark energy might instead be determined by a very strange property of our universe, which was first predicted by string theory. Thus, many scientists are inclined to call the DESI results the first observational confirmation of this theory, one of the most viable current candidates for the title of the theory of everything, the holy grail of fundamental physics. In other words, the new data call into question the lambda CDM cosmological model, which has dominated modern science for the last 25 years. But they open entirely new horizons in cosmology, quantum physics, and, if you think about it, physics as a whole. In today's video, we will examine what exactly the Dark Energy Spectroscopic Instrument DESI has discovered, how and why its data was interpreted in this particular way, why it is said to refute the lambda CDM model, how it supports the conclusions of string theory, and how this discovery could radically change all of modern physics. But one thing at a time. On March 19th, 2025, at the Global Physics Summit of the American Physical Society in Anaheim, California, the team of scientists working with the Dark Energy Spectroscopic Instrument announced that their data indicates a decrease in the acceleration with which our universe is expanding. Specifically, they concluded that 4.5 billion years ago, this acceleration was approximately 10% higher than it is now. And this evidence alone claims to be yet another revolution in cosmology. And to understand why, we need to delve a bit into the history of the subject. In 1917, Albert Einstein published his general theory of relativity, essentially a theory of gravity describing the gravitational behavior of any distribution of energy in space, for example, rest energy, that is, mass. Among other things, Einstein's equations were supposed to describe the behavior of such a system of energy and mass distribution as the entire universe. In 1922, Soviet physicist Alexander Friedmann solved Einstein's equations for a quantity known as the scale factor, which in cosmology is usually denoted by the letter A. Let me explain what this is. If, at the initial moment of time, the distance between 2 points in the universe's space was equal to r0, and after some time t it became equal to r of t, then the scale factor would be equal to the ratio of r of t to r0. I emphasize, we are talking specifically about points in space itself, not about the relative positions of objects located at those points. These objects may have some relative velocity with respect to each other, or they may be motionless. But even in the latter case, the distance between them will change simply due to the expansion of the universe's space. More precisely, from the perspective of Friedmann and Einstein, it would be more accurate to say may change due to the expansion of space. For instance, Einstein himself, like most of his fellow physicists, considered the universe to be stationary, that is, unchanging in time. In such a universe, the distance between its points should not change, meaning the scale factor should be equal to 1, or at least be a constant value. However, Friedmann, having solved Einstein's equations, showed that the scale factor almost certainly cannot remain constant. To be more precise, the first Friedmann equation gives us an expression that relates the rate of change of the scale factor, that is, its time derivative divided by the scale factor itself, to key parameters of the universe, such as the energy density distribution in space and the curvature of the universe's space. Essentially, this very quantity can be interpreted as the expansion rate of the universe. The second Friedmann equation describes the rate of change of the expansion rate, that is, the acceleration of the universe's expansion. It turns out to depend first on the same energy density and second on the pressure exerted by the substances possessing this energy. At the same time, energy density and pressure are related in a specific way, like this, where omega is the so-called equation of state parameter, which depends on the type of substance with the given energy density. By expressing pressure in terms of energy density using the equation of state, we can rewrite the Friedmann equation in this form. For known types of substances, its value ranges from 1/3, for electromagnetic radiation, i.e. a photon gas moving at the speed of light, to 0 for ordinary matter. And this is the key takeaway for us. Omega in the Friedmann equation must either be positive or at least non-negative. Now, let us ask the question, can the Friedmann equations describe a stationary universe? Under all conceivable conditions, the answer to this question will be no. As we have already said, in a stationary universe, both the first and second time derivatives of the scale factor must fundamentally be 0. The first Friedmann equation can give us 0, but only under a very specific relationship between space curvature, energy density, and the value of the scale factor. If the density is slightly higher or lower, or if the scale factor is slightly smaller or larger, the equality no longer holds, and we end up with either a contracting or an expanding universe. In other words, from the perspective of the first Friedmann equation, a stationary universe is possible only under an extremely precise tuning of its parameters, a scenario that is not so much unrealistic as it is highly dubious. However, if we also take the second Friedmann equation into account, the situation becomes even worse. Indeed, according to the second Friedmann equation, the acceleration of the universe's expansion can be 0 in only 2 cases. Either if the energy density in the universe is 0, meaning the universe is completely empty, and we know this is definitely not true for our universe, or if this term in parentheses equals 0, i.e. if the equation of state parameter of the universe is equal to -1/3. However, earlier we stated that the equation of state parameter should not be negative. This means that this expression will always be positive, and the acceleration of the universe's expansion will always be negative. This means that, according to Friedmann's equations, the expansion rate of a universe filled with ordinary matter and energy cannot globally be 0. Even with fine-tuning of the universe's parameters, a state of 0 expansion speed can only be fleeting, just as a stone thrown vertically upward momentarily comes to rest at the peak of its trajectory. In other words, analyzing Friedmann's equations for describing the real, observable universe automatically leads us to the conclusion that at some point in the distant past, there must have been a moment when the universe, having practically 0 size, or more precisely, a 0 scale factor and nearly infinite density, began expanding from this state at a very high but gradually decreasing speed. This scenario is what we now call the Big Bang scenario. However, many of Friedmann's contemporaries, including Einstein himself, had serious doubts about this idea. The belief in a stationary, eternal, and unchanging universe was too deeply ingrained. To address this, Einstein modified the equations of general relativity by adding another term dependent on a certain constant lambda, which he called the cosmological constant. Accordingly, Friedmann's equations were also modified, taking this form. With the right choice of the cosmological constant, it now became possible to obtain not only a 0 expansion rate for the universe, but also 0 acceleration of expansion. The theory of a stationary universe seemed to be saved. Einstein's triumph was short-lived. By the mid-1920s, astronomers had established that the universe was not stationary but expanding, precisely as one would expect from the original version of Friedmann's equations. To be more precise, Edwin Hubble and Milton Humason measured the distances to 24 nearby galaxies, located between 1 and 16 million light-years away, and then measured the redshift of the light from these galaxies as it traveled to us, which allowed them to determine their recession velocities. It turned out that the recession velocity was directly proportional to the distance to the galaxy. Considering that we are not talking about ordinary mechanical recession, but rather recession due to cosmological expansion, that is, the increase in distances between points in space itself, we can see that the ratio of recession velocity to distance is nothing other than the ratio of the time derivative of the scale factor to the scale factor itself. And this ratio, according to Friedmann's equations, should indeed be constant for all points in the universe at a given moment in time. That is, for the current values of the scale factor and the universe's density. In simpler terms, It turned out that Friedmann's equations without the cosmological constant perfectly described the observable universe, making the introduction of this constant unnecessary and redundant. Einstein, who later fully acknowledged Friedmann's correctness, called the cosmological constant the biggest blunder of his scientific career. Friedmann's idea of an expanding universe became widely accepted in cosmology, an event now called the First Cosmological Revolution. Equally accepted was the logical consequence of Friedmann's equations, the idea that the universe's expansion must be decelerating, meaning the Hubble constant should decrease over time. Once Friedmann's theory of a decelerating, expanding universe became dominant, physicists sought to determine how exactly this deceleration occurred. At the very least, knowing this would allow them to plug the value into the second Friedmann equation and learn much more about the universe. For example, its average energy density, composition, equation of state, and even its ultimate fate. Would the expansion slow indefinitely, asymptotically approaching zero? Or would it eventually reverse, leading to a big crunch where the universe collapses back into a singularity? Unfortunately, for decades, measuring the deceleration of cosmic expansion remained an unsolved problem. To determine how fast the universe was slowing down, scientists needed to measure its expansion rate billions of years ago and compare it to today's value. This wasn't entirely impossible. Astronomers didn't need a time machine. They just had to observe objects billions of light years away, seeing them as they were in the distant past. Roughly speaking, astronomers needed to extend Hubble's linear velocity-distance relation to much greater distances. In a decelerating universe, this line would curve downward at large distances, and the degree of curvature would reveal the rate of deceleration. In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, measured distant Type 1a supernovae in galaxies 7 to 8 billion light-years away. The results were shocking. Instead of curving downward, the velocity-distance relation bent upward, as if the universe's expansion was accelerating, not slowing down. As soon as this discovery became known, cosmologists realized that Friedmann's model needed a major revision. The implications were profound. Something mysterious was counteracting gravity on cosmic scales. Indeed, the second Friedmann equation only permits accelerated expansion of the universe if it's filled with something possessing an extremely exotic equation of state with a state parameter less than -1/3. However, as we've already discussed, for all known forms of energy, the equation of state parameter cannot be negative. This unusual, exotic form of energy with such an atypical equation of state is what cosmologists called dark energy, and now they needed to understand what it actually was. Here, they were helped by the largely forgotten work of Soviet physicist Yakov Zeldich, who back in 1967 had predicted something similar based on quantum mechanical considerations. In one of our previous videos, we discussed how even in a complete vacuum and in the absence of any fields, so-called virtual particles constantly emerge from nothing and disappear again. In other words, if we were to photograph even empty space at any given moment, we would always detect some particles possessing mass and therefore energy. This means the vacuum itself must possess energy and mass. Put simply, space itself, independently of anything that might be within it. Zeldich showed that this vacuum energy would be characterized by an equation of state with a negative parameter, specifically equal to -1, making Zeldich's vacuum energy an excellent candidate for dark energy. If we formally add the vacuum energy density and its corresponding pressure to the second Friedmann equation, apply Zeldich's proposed equation of state, and then expand the terms, we obtain an expression of this form, differing from our earlier version of the Friedmann equation by the final term. This term is positive, and if the vacuum energy density is sufficiently large, we get exactly what we need: accelerated expansion of the universe. Thus, Zeldich's hypothesis could explain the accelerated expansion and modify Friedmann's equations to match observations. So physicists seem to have figured out how the universe could be expanding with acceleration. But this leads to the next question. How does this acceleration change over time as the universe grows larger and larger? In Zeldich's theory, the vacuum energy density shouldn't change as the universe expands. Indeed, cosmic expansion is essentially creating more vacuum. And according to Zeldich, the same volume of vacuum should contain the same amount of energy. Just as adding more water to a glass increases the amount of water but not its density. On the other hand, the density of ordinary matter, which counteracts the accelerated expansion, should decrease as the universe expands, much like juice becomes more diluted when we add water. In other words, the acceleration of cosmic expansion should increase over time, gradually approaching some constant value. Thus, in Friedman's universe, where Zeldich's vacuum energy plays the role of dark energy, the acceleration of cosmic expansion should only increase. The DESI collaboration set out to test this prediction and ideally measure the magnitude of this increasing acceleration. The principle was essentially the same as in previous studies: measure distances to cosmic objects and their recession velocities from Earth observers, then analyze the results. But this time, researchers needed to peer even deeper into the past, to distances of about 10 billion light-years and beyond. When they succeeded, another surprising discovery emerged. The universe's expansion acceleration appeared to be decreasing over time, as if the concentration of dark energy was diminishing with cosmic expansion, which shouldn't happen if we understand dark energy as Zeldich's vacuum energy. Just in case, let me emphasize, the DESI observations do not question either the expansion of the universe or its accelerated expansion. And if that is so, the cosmological model consistent with the DESI observations must still include some explanation for this accelerated expansion, that is, its own notion of dark energy, or something analogous to it. However, within this explanation, there must now also be an account for how the density of this very dark energy can decrease as the universe expands. Fortunately, theoretical physicists already have several ideas on this point, and the most interesting among them is the one proposed in the mid-2010s, which is related to a very relevant scientific theory known as string theory. To understand what it is about, we first need to return to the most basic concepts of school geometry. For example, suppose we want to find the area of a rectangle. This is a rather simple task. First, we must determine the length of one of its sides, then measure the length of the side perpendicular to the first one, and then multiply them. But what if instead of first determining the x-coordinate and then the y-coordinate, we do it in reverse order? That is, measure the y-coordinate first and then the x-coordinate. Obviously, this switch will not affect the result. Mathematicians say that multiplication possesses the property of commutativity, that is, x times y equals y times x, or, if you prefer, the difference between x times y and y times x equals 0. However, multiplication is not always commutative. For instance, the operation of vector multiplication is non-commutative. In it, a cross b equals minus b cross a. The multiplication of matrices is non-commutative, as is the composition of functions and several others. Nevertheless, the multiplication of coordinates, which are scalar quantities, in the geometry we are used to, is always commutative, and it would seem there is nothing to discuss. However, mathematicians enjoy finding something to talk about even in the most obvious cases, and so they decided to ask, what if the operation of coordinate multiplication turned out to be non-commutative? That is, x times y minus y times x equaled not 0, but some other value, for example, like this one. This is how the branch of mathematics known as non-commutative geometry emerged, with its foundations laid in the 1980s. It turned out that in such mathematics, many familiar mathematical or even arithmetic operations need to be reformulated, and the results of such operations differ greatly from those we are used to. And all this would have remained a rather abstract, though amusing, mental exercise had physicists working on string theory in the 1990s not come to the conclusion that certain versions of this theory must be described precisely by means of non-commutative geometry. I will not explain exactly how non-commutative geometry appears in string theory. Unfortunately, I am not among the few hundred people on Earth who understand this theory well enough. And besides, this video is not the place or time for a deep dive into string theory. I will only say that once string theory was found to be connected to noncommutative geometry, it became clear that a universe described by string theory could also have a noncommutative geometry. And so many familiar equations must be rewritten using the developments made in this field. In regular quantum mechanics, we also deal with non-commuting quantities, for instance, the coordinate of a particle and the projection of its momentum on the same axis. From this directly follows the Heisenberg uncertainty principle, which states that the coordinate and momentum of a particle cannot both be measured with absolute precision. I will not now explain how this principle follows from that definition. I will just say that such a result directly arises from the very definition of non-commuting quantities. And in a universe where different coordinates do not commute either, a similar relation must hold for them. To be exact, since the commutator of coordinates equals such a value, then the coordinates themselves can only be determined with precisions whose product cannot be smaller than that value. And if in quantum mechanics we say that we cannot simultaneously determine a particle's coordinate and momentum with absolute accuracy, then in string theory, more specifically, in those versions where non-commutative geometry arises, we cannot even determine the coordinates themselves with perfect accuracy, meaning we cannot precisely define a particle's position in space. To be exact, the most we can say is that the particle is localized within a certain small rectangle. In essence, the entire space of the universe ends up divided into such rectangles. In other words, it becomes like a lattice, quantized structure. The size of these little cells turns out to be extremely small. The side length of one such cell is on the order of the Planck length, which is 10 to the power of minus 35 meters, which is roughly a trillion trillions times smaller than the diameter of a hydrogen atom. Our measurement instruments are not precise enough, and will not become precise enough anytime soon, to measure quantities with such precision, so we cannot directly probe the granularity of space and test this prediction of string theory head-on. Fortunately, the physics of a universe with non-commuting geometry must also have other distinctions. For example, the second Friedmann equation, in its very first original form without any additions involving dark energy, in a universe with non-commutative geometry, must acquire an extra term in the form of a function depending on the non-commutativity scales. And it turns out that this term must be negative, meaning that if its absolute value is large enough, then the whole expression inside the brackets becomes negative, and the acceleration of the universe's expansion becomes positive, essentially just as it happened when dark energy was added to the Friedmann equations. In other words, the acceleration of the universe's expansion appears in non-commutative versions of string theory kind of by itself, and no extra entities such as dark energy are needed to explain it. That is, it might turn out that no dark energy exists at all, and what we previously believed to be a manifestation of its presence is in fact just a mathematical artifact, arising because we were using equations that were not entirely correct. Unlike vacuum energy, whose density should remain constant, dooming the universe to faster and faster expansion, the correction associated with non-commuting geometry is likely to decrease with time, more precisely as the universe expands. Why should it decrease? Let me explain it using an extremely simple, although not fully accurate, analogy. We remember that the non-commutativity of the universe leads to a granular structure of space, and the size of each elementary cell of space turns out to be fixed. The larger the space of the universe becomes, the less distinctly individual cells will be seen in it. When looking at the sea up close, we can make out the crests of individual waves. At greater distances, the surface appears to have a slight ripple, and from a great height, the surface of the sea seems perfectly smooth. In just the same way, as the scale factor increases, that is, as the universe expands, the irregularities of space caused by its non-commutative geometry must become smoothed out. And therefore, the contribution of this non-commutativity to the second Friedmann equation must diminish. And along with it, the acceleration of the universe's expansion must also decrease. And the fact that DESI observed precisely this kind of evolution of the universe can be considered, albeit indirect, still a real confirmation that string theory actually applies to our universe. And if so, then this will be the first observational evidence of that theory, which until now had remained beautiful but nonetheless abstract. That is exactly why the DESI findings, which shocked cosmologists, so delighted supporters of string theory. Alas, as often happens with news from the world of science, it is best not to rush to conclusions. First of all, based on DESI data alone, it is still too early to confidently assert that the acceleration of the universe's expansion is decreasing over time. The confidence level of DESI's results ranges from 2.5 to 2.8 sigma, meaning they exceed the measurement error by a factor of 2.5 to 2.8. In modern physics, it is customary to say that a discovery can only be claimed when the confidence exceeds 5 sigma. Unfortunately, DESI's results fall short of this threshold, and in order to speak with certainty, we will apparently have to wait for new, more precise observations. Secondly, string theory and noncommutative geometry are not the only models capable of explaining an accelerating universe with a decreasing rate of acceleration over time. So unfortunately, it is still too early to claim that the decrease in cosmic acceleration necessarily points to the correctness of string theory. Not to mention that not all versions of string theory imply a non-commutative geometry of the universe. Nonetheless, even now, DESI's data represent extremely valuable, interesting, and intriguing information, and it may well be that the year 2025 will go down in history as the year of a new revolution, not only in cosmology, but also in other areas of physics. Let us hope we will not have to wait too long for further studies that will bring more clarity to this issue. Then again, we do not really have time to be bored while waiting, because the mystery of dark energy is far from the only unsolved puzzle of our universe. In closing, I would like to thank the sponsors of our project here on YouTube, as well as on our pages at Boosty and Patreon, and invite everyone who enjoys what we do on this channel to support our work. All the necessary links for that will be in the video description. And that is all from me. All the best, dear friends, and see you next time.